All right, thanks. So that's what I'll be talking about today. So a little bit of background and motivation for this. So histotripsy, as most of you know, is a non-thermal ultrasound therapy that relies on generating targeted cavitation events to fractionate tissue. And we've previously demonstrated in transcranial studies that we can target accurately to within a millimeter of the focal spot that we intend to, and that we can treat large volumes rapidly. So we've achieved treatment rates of up to about 10 cc's per minute. But it's kind of an open question, how do you monitor these treatments in transcranial therapies? And it's possible via MR methods, but histotripsy is not a thermal therapy, so MR isn't really ideal. And you want to be able to monitor pulses on a pulse-by-pulse basis because every single one is able to do damage. So we want to develop a method that can reliably localize and monitor treatments in real time that isn't MR-based. And so the way that we are working on doing that is using what we call acoustic cavitation emission feedback. And so what you see here is a video of a histotripsy pulse propagating from a transducer at the bottom of the image to the focal point in the center where it nucleates a bubble. And when the bubble is nucleated, it emits a shock wave that radiates outward that we can monitor to localize those bubbles. So in a typical experiment, you might imagine you send your ultrasound pulse through the skull to the focal point of the transducer to nucleate a bubble. It sends out a shock wave, travels back to the transducer, where it excites the transducer element in a way that you can measure the signals and then use those signals to localize the bubbles. And so to demonstrate our ability to do that, we ran some experiments where we were generating bubbles through the skull and using those signals to localize them. And so what you see here is a picture of our experimental setup, which is we use a hemispherical phased array transducer, 30 centimeter aperture diameter. It's 256 elements with a 500 kilohertz center frequency. Of those 256 elements, we use 160 of them as receivers to receive the emission signals from those shock waves, so that we localize bubbles based on those received signals, and then to experimentally verify the positions of the bubbles that we localize using those signals. We made measurements of the position of the focal point using either a hydrophone or images of the bubbles from 2 orthogonally mounted cameras so that we could measure the 3D position of the bubbles during experiments. So to localize the bubbles based on those signals that we received, we did essentially a volumetric signal intensity mapping where we would project the signals that we measured back from the array towards the focal point of the transducer as propagating spherical waves with a constant sound speed. So we ignore the presence of the skull in the beam propagation path. The mapped region for the localization was centered about the expected focal point of the transducer. The volume that we were mapping was 21 millimeters wide, composed of 64 by qubit elements. To generate the signal intensity map, we would just sum up the amplitude of the signals that we measured at each element within that volume, and then to localize the bubble, it was an intensity weighted map of the volume above the 3 dB level. And so here what you see is some of the results of this localization algorithm that we did. So the first thing I'm going to present is the comparison of the localization versus hydrophone measurements. And what you see here is the results of that from through 2 separate skulls at 3 different PRFs. And so you can see in general that the localization that you get from projecting these signals back is in very good agreement with the measurements from the hydrophone through both skulls and at all the different PRFs. And you see in the lateral direction, the position of the bubbles is pretty spot on, but there's a prefocal axial shift in the localization compared to what the measurements from the hydrophone show. And looking at it as a function of PRF, you see that the error goes up with PRF, but it's within a few hundred microns, and between skulls it's pretty consistent as well. Taking a look at the images, what you see here are images of bubbles generated at 1, 10, 50, and 100 hertz. And you'll notice that the size of the bubbles actually does go up as a function of the PRF, and so the error should correspondingly go up as well. If you look at the results compared to the imaging, what you see here is the comparison of the ACE localization to the 3D imaging results through the skull at 1 and 100 hertz. And so the green blobs are the projected volumes of the bubbles measured in camera images, and the blue dots are the localization results. And you can see, aside from a few outliers, the localization results are really pretty close to what we see with the camera imaging, either within the volumes that we measure or very close to their peripheries. And so with that, that's just a summary and conclusion. So we were able to get generally good agreement with the measurements from hydrophone and cameras less than about 1.5 millimeter separation. In general, compared to the camera images, we were within 0.5 millimeter of the boundary, and consistent between experiments looking at the different combinations of skull, location, and PRF. The error increased with PRF, but it was bounded to within the size of the bubbles that we actually did measure, so it's still pretty accurate. And then computation time for this, it takes about 10 milliseconds to do this localization, so we can do real time up to 100 hertz, and the algorithm scales effectively with GPUs, so we should be able to get faster with better GPUs. And so with that, I'd like to acknowledge everybody and take questions.
So how can I monitor the tissue change, not the bubble?
How can I monitor what?
Tissue change.
So at the moment, I don't have a good way to do that. One of the things that you could potentially do is what you see in the water, at least with the imaging, is that the size of the bubble gets larger at a higher PRF, but in tissue, the motion of the remnant bubbles is restricted. So the size of the bubbles initially should be small, even if you are running at a higher PRF. So one potential way to monitor for tissue damage is to look at when your precision error starts to increase, but that's just speculation for right now.
Thank you.
Go ahead.
All right. Yeah, hi, nice talk. So just a very simple question. Have you done, I know you didn't present any, but have you done any kind of ex vivo tissue that you've placed in the region of the focal zone? And my question actually is directed at, are you seeing the same kind of sharp margins that you typically see in your kind of outside of the brain applications that, Charles has presented in the past?
So I mean, with the localization stuff, I haven't done that, but we can run it at the higher PRFs and still see the pretty sharp boundaries in at least phantom studies, yeah. So.
Thank you.
Yep.
Just back on the question of tissue changes, wasn't there some work showing that you can see when the cell membranes are breaking on diffusion-weighted MRI?
Good question. I'm not 100% sure.
That's all right.
So.
Okay, I'm just curious. I know diagnostic ultrasound pulses and images, but I was thinking there might be more of a problem with a very high-intensity pulsed transducer to have it also receive. And are there issues that had to be addressed that?
It's been a very frustrating process. Yeah, I mean, it's one of the things that is the real challenge is that the emission signals are 3 kilovolts amplitude, and the signals that we receive from the bubbles are 10 millivolts. Mm-hmm. So we had to, it goes through a nonlinear compressor, so we can see the signals that are kilovolts as well as the signals that are small amplitude, but that's created its own problems. I mean, we could talk more about it. It's been frustrating, but it's rewarding.
I think you should be commended for doing this.
So,
very good. Thank you very much.